Welcome everybody to this presentation. On the 19th of July 2021 I did a post on Facebook about the wind turbine that I designed and built. I'm inspired how many people showed interest on that, and I thought because of that I'll try and give a little bit more detail. In this presentation I show how the alternator of a wind turbine, in other words alternator, we can see that here on the left hand side, how I combine the alternator together with a solar panel. That gets done in this controller here, and then just for demonstration purposes here I've got a small lead acid battery. This is a 7 amp hour lead acid battery, and it's I think it's a 10 watt solar panel. Now just to note, in our house the way we operate this, I use a flooded lead acid battery. It's a 150 amp hour golf cart battery, so it's obviously a lot bigger than this. I charge that with 2 wind turbines and 2 solar panels. The solar panels each have got I think 90 watts. Yeah. Okay. The other thing that's also important to me to say here is many people would have seen this wind turbine presentation and would actually like to build the machine. I realized that most people won't have access to a lathe and a milling machine and engineering tooling like I've had access to. And I want to therefore encourage people to go onto Hugh Piggott's website. I'll see that I can put either the name or the link in the comment below to this post. He has really excellent building plans for wind turbines, which I can say out of own experience I've built one of his designs which work very, very well, and it's been running at my house or our house for a number of years very successfully now. So please have a look at Hugh Piggott's designs and his instructions for building wind turbines. Those are machines people can build successfully without any sophisticated engineering tools. The concepts that I'm going to show in this video is very much the same, if not identical, to the concept he uses in his designs. I think it would be fair to say that I've actually learned 99.9% what I know about wind turbines from his website. So yeah, just again to recap, on the left hand side here we've got a low speed alternator. What do I mean by low speed alternator? It means it starts generating power at even a rotational speed that's very low. That's important so that it can start generating electricity in relatively low wind speed. Then we've got the charge controller, which I'll explain a little bit more shortly. This is the charge controller for a wind turbine is inside this box here. The charge controller for the solar panels at the bottom here. Then obviously we've got the lead acid battery, and we've got the solar panels. Yeah, so in my experience it actually only makes sense to combine the solar power and the wind power. It's not that the one's better than the other, it just is sometimes there's sun and sometimes there's wind, and sometimes you have days where it's overcast and you don't see the sun but it's windy, then the wind turbine will continue charging the battery, and there's some days there's no wind and then the sun will, and some days there's both, so it just depends. Anyway, we have from the alternator we've got 3 phases coming out, and that's going to the box here. Just excuse me a second, I'll be back in. Apologies about that. Just had to actually let our dogs out the house. They were getting a little bit restless. Yeah, so we've got three phases running from the alternator going to these inputs here. Inside the box we've got a rectifier. The rectifier is basically, it's about the size of a matchbox. 3 contacts in with 2 out. It changes the alternating current to direct current, which is then used for charging the battery. On the left top here we've got an ammeter that would show how much charge the wind turbine is delivering, and on the right hand side we've got an ammeter which would show how much charge the solar panel would be delivering. Then in the middle here we've got a digital indication. I'm not sure whether one can see this on the video. It shows 13 volts at the moment. It shows the battery voltage. So that would mean the battery is at the moment fully charged. A battery voltage of 12.8 volts would mean that it's fully charged. If it's going higher than that, that means that there's a little bit of an inflow of current to the charge, to the battery. So then at the bottom here we've got an ammeter which shows how much current is on the load. Now to demonstrate that, I've connected a little hobby jigsaw to this. If I now run, this is a 12 volt saw by the way, if I run it, I can see the needle goes up to just under 2 amps, and the voltage obviously drops a little bit. So having indications like this is useful, because this means if I operate the system from day to day, I can see how much current am I getting from the turbine, how much current am I getting from the solar panel, what's the condition of my battery. I can also see how much current I'm using. So I can, for example, see, am I using more current than what I'm charging, or am I charging more than what I'm using. That's useful. So yeah, so just to recap, we've got 3 phases from the alternator going into these 3 connections. Then it goes internally into a rectifier, 3-phase rectifier, which then transforms the alternating current to direct current to charge the battery. On the right hand side here we have 2 inputs for the solar panel. We've got the battery over here, and we've got the output over here, and then at the bottom the solar controller. Now something that is important to note here is the controller for the solar panel is different than the controller for the wind turbine. With the solar controller, what happens is if it senses the battery is fully charged, and that happens around about somewhere between 14 and 14.5 volts, what the solar panel controller does, it simply disconnects the panel from the battery, and when it senses that the battery requires charge again, it connects it again. The wind turbine controller has to be different, and the reason for that is that if the controller would hypothetically disconnect the alternator from the battery, then it would spin very freely. I can demonstrate this through turning it like this. You can see there's no friction actually, because at the moment there's no load on the alternator. So if you had a very strong wind and your controller disconnects the alternator from the battery and there's no load, then what can happen and will happen is that the RPM will go so high that the centrifugal force will actually like tear the blades off the machine, would destroy your machine, and it would be dangerous. Now the reason why it's turning so freely at the moment is because at this speed it has not yet reached the battery voltage. Perhaps what I can show there, which might be helpful, is I'm going to first of all now disconnect the solar panel from the controller. Now note, when I disconnect things here, it's important that the battery is on without the solar panel. In other words, not the other way around. I mustn't first go and disconnect the battery and then the solar panel. The reason for that is that the open circuit voltage of a solar panel, sometimes when it's sunny, I've seen it go up to about 22 volts. Okay, so what does open circuit voltage mean? It means basically if there's no load, in other words, if there's no load on the solar panel, what voltage would I measure? And in this case, as I mentioned, I've seen up to 22. Now that voltage would be enough to destroy the electronic components, or some of the electronic components, which I've used to build the controller. What happens is, if I have the battery on there and I then connect the solar panel, the battery actually stops the voltage from rising too much higher than what the battery voltage is. In other words, I would probably hardly see a voltage higher than 14.5 volts. So remember that. Always, if you are disconnecting things, always the solar panel first, then the battery. When it's connecting things, it's the other way around. It's the battery first, then the solar panel. Right. So the solar panel is now disconnected. The next thing that I'm going to do is I'm going to disconnect the battery here. So now once that's done, there's no power at all going to this unit. What I'm going to do now is I'm going to take this analog voltmeter. I'm just going to make sure I get the polarity right. I'm going to connect this here very temporarily. I'm not sure whether one can see the needle on the movie or not, but I'll call out the numbers as I see them. What I'm going to do is turn the alternator, and as I turn it, I can see that the voltage is rising. So if I'm turning it like this, I'm seeing about 2.5 volts. And this meter goes from 0 to 15 volts. So I'm turning it, and you can see even if I'm turning it like this, I've already reached 5 volts. Now I've reached 6 volts. So basically, if this machine had to turn twice as fast as it's turning now, it would then reach the battery voltage with about 12.8. Sometimes that speed is spoken about as cut-in speed. Now, this is also something that makes this alternator very interesting, because it means at startup, in other words, let's say for example there's no wind, and then slowly on the wind starts blowing, there's actually hardly any other friction than that what the bearings present. That's very helpful because it means aerodynamically the blades of a wind turbine, which mount onto the front here, can then actually take up a speed where the angle of attack on the blades is ideal and where a lot of power can develop. So let's think about that again. The wind starts blowing, the machine starts turning. At the moment there's no friction. It goes faster and faster, and then eventually, as it reaches battery voltage, around about 12 volts, give or take, that's when then actually resistance will start happening, because only then at that voltage will the alternator start to charge the battery. So also important there to see, if the machine is turning at a speed which brings a voltage below 12 volt, it's not charging the battery yet, it's just idling, it's kind of getting ready to charge. Alright, so again, just to have a look, as I'm turning, as I'm going faster and faster, the voltage rises more and more. But importantly, it's built in such a way that it starts producing current at very low RPM. Alright, We can do a couple of experiments with that, just for interest's sake. I'm going to now take this meter off, and then I am going to take these phases off here as well. What I'm going to do now is I'm going to flick the machine to turn, so you can see it's turning. And I'm going to short circuit two of the phases. And you can see that that's practically like putting on the brakes. We'll do that again. So you can see it actually, what happens there is that the magnetic forces build up in the coils, and that acts a little bit like a brake. So a similar thing happens, not quite as extreme obviously, but a similar thing starts happening when the alternator reaches its cutting speed at just over 12 volts and the battery starts charging. So that actually stops the machine from overspeeding. Okay, so that's why the charge controller for the wind turbine has to be different. Whereas the solar controller simply electrically disconnects the panel from the battery. What the controller for the wind turbine needs to do is it needs to keep the battery connected to the alternator all the time. What it does to stop the battery from overcharging is it actually directs some current into these resistors, which I've got 3 of at each side there. Those resistors look like this here. They're in aluminium, 50 watts, 6.8 ohm each. They get rather hot when the current is directed to them. That's why I mounted them on these little stainless steel plates here. So pragmatically what one gets is the turbine charges the battery when the controller senses that the voltage reaches somewhere between 14 and 14.5 volts. It through a relay directs current to the resistors. Once the voltage drops to about 13.5, it then switches off the power to the resistors again, and it allows the battery to charge up again to about 14.5 volts. It then again directs the power to the resistors until the voltage of the battery drops to 13.5, etc., etc. So when the turbine is working hard, one gets this on and off clicking of the relays directing the power to the resistors. So what I'm going to do now is I'm going to open this box to show you what it looks like inside here. The controller that I've got on here I built according to the plans from Hugh Piggott of his website. As I mentioned, please go and visit that very, very interesting website with lots of information there. You can see the controller over here, so in this area where I'm pointing with a screwdriver. So that just senses the battery voltage, and then as mentioned, when the battery voltage reaches 14 to 14.5 volts, which one can set quite precisely on these potentiometers, it then directs the power to the resistors over here. Alright, then also of importance here where I'm pointing now with a screwdriver, this is the rectifier. So that's a little black box with connections for the 3 phases going in, and then 2 connections for the direct current going out. It's mounted on an aluminium heatsink because it gets hot during operation. So, I mean, that's very simple device. It's about half the size of a matchbox, and it's also readily available from electronics stores. This wiring in here, it might look very overwhelming. What I can say is, if you build this yourself and you just go about it step by step by step, it's actually not that bad. It's really quite doable. So we'll put this cover back on here. So you can see what we're doing with this box is we essentially combining the solar panel power with a wind turbine, and we're also using it to rectify the alternating current and control the charge control, to control the charge to the battery from the wind turbine. I hope that's useful information. I really just like to encourage people who are interested in this sort of thing. One can build your own wind turbine. It's an interesting project, a lot to learn. And it's actually an enjoyable hobby with the product electricity at the end of the day, which is useful. In our house we run our lights from our own power. What we use are these LED downlights, and the great thing about these is their current draw is minimal. In our house I think we've got a total of roughly 16 of these, and I've measured if I switch all of them on at the same time, there's a draw on the battery between 7 and 8 amps. So I mean, it literally means if I'm switching the whole house, everything on, and I run it for 6 hours, that brings me to about 50 amp hours of power that I've drawn out of a 150 amp hour battery. Means like I've depleted about 1/3 of the battery, which, I mean, it's great. That one shouldn't really go too much deeper if one wants to. What I mean by deeper, one shouldn't really draw too much more power out of a battery if one wants it to last for a long time. But these lights are great. They are bright, and it keeps the lights on during load shedding, which is fantastic. So I hope this is helpful, and like I said again, please go onto Hugh Piggott's website as well. Maybe you find a drawing or plan there which you can build your own machine from and make your own power. And thank you for watching.